So it's a great pleasure for me to introduce my friend and collaborator, Professor Keigo Fukumura. Keigo obtained his bachelor in physics from the Kyoto Sanjo University in Japan. Then he moved to the US to get his PhD in physics from the Montana State University. From 2006 to 2012, he was first NPP fellow and then research associate at NASA Goddard Space Flight Center. We were actually office mates for a couple of years. Then in 2012, he moved to the Physics and Astronomy Department of James Madison University, where he is now associate professor. Keigo is one of the world experts in modeling MHD winds from accreting black holes, and today he's going to tell us about MHD diagnostics of X-ray outflows from black hole accretion disks. Please, Keigo, go ahead.
Okay, thanks so much, Francesco. So I'm going to screen share, and I'd like to start with a little bit of acknowledgement first. So I hope you can see the screen there.
Yes.
Good. Okay, good. Thank you. Okay, so good afternoon, everyone. I'm Keigo Fukumura from James Madison University in Virginia. First, I'd like to thank the seminar organizers, Marina, Francesco, and Ajay, even though Ajay is not here, for inviting me to this seminar opportunity. And so I am very happy to be virtually here with you, the audience, and I also want to thank the audience for taking your time to be here. And it's my pleasure to speak to you all today about the black hole accretion disk winds, both in X-ray binary systems and also the AGN environments, which draws a lot of attention and exciting interest in the high energy X-ray astrophysics community, especially in anticipation of the upcoming new X-ray telescopes such as XRBs and Athena. So today, maybe my talk is a little bit biased towards my personal perspective about how and what those black hole accretion disk winds might be, and hopefully you can agree with some of my viewpoints. So, of course, I am collaborating with lots of wonderful people around the globe, including the people there at Vergata. I hope I'm not pronouncing wrong. Francesco and Ajay. And this is also in collaboration with the Athena Science Working Group, Physics of Accretion group. And I'm getting a lot of interesting implications and suggestions and ideas from these wide range of collaborators. So just want to acknowledge those people. Okay, so please, if you have any questions or if you need to stop me at any point, please do so, and I will stop and then explain and describe whatever you may have. So here's my outline. To start, I would like to briefly just explain what kind of accretion disk winds I am interested in from both observational point of view and the theoretical perspective. My talk will be primarily focused on these two types of outflows, warm absorbers and ultra-fast outflows. And as I said, our group has been engaged in developing the accretion disk wind models with the focus on magnetic driving scenario. So I would like to introduce what that model is, and then as everybody gets excited in X-ray astrophysics community, I'm going to show some of the simulations expected from the CRISM Resolve instruments and also the Athena X-IFU data. And then I will finish my talk with the takeaway in the end. Okay, so what do I mean by outflows of black hole accretion disk winds? Well, so here up front, I'd like to make it clear that I am not going to talk about jets, which is essentially dominated by the synchrotron processes by electrons that can be detected and observed by radio observations. But my outflows are ion-dominated accretion disk winds. So it's not the Poynting flux dominated electromagnetic jets. And the accretion disk winds are typically not really collimated, but it has a very wide opening angle. And there is a number of reasons to believe that these outflows, these accretion disk winds, are intrinsic to the compact objects, and they are most likely originating from the disk itself. And of course, we see these outflows primarily in X-ray band. Okay, so let me just start with some of the observations and the data we have today. Okay, so the ionized outflows are ubiquitously present in many, many different environments in the universe, ranging from low ionization state to high ionization states. And I'm going to talk about the ionization state in a moment. In AGN and X-ray binary systems, we see these absorbers, ionized absorbers in X-ray bands, but we also see ultraviolet absorption lines in these systems, in addition to bright quasars at the cosmologically distant locations. From the spectrum, both in UV and X-ray band, we know that there is a number of chemical elements. We see a series of very rich contents made by the chemical elements that we see in the chemist's periodic table. So we believe that these ions are present along our line of sight. When you look at the trough energy or the centroid energy of these absorption features, those are blue-shifted, and that's how we know that they are coming out of the system. And most of the features are bound transitions, which is resonant transitions. So I'm not really going to talk about the edge features here. So in order to better understand these ionized outflows, people typically use those three physical quantities, which is quantum density and sub h. So this tells us the number of atoms per square centimeters along this line of sight. We don't know exactly where they are along the line of sight, but we can estimate how much material is present per square centimeter window. We can also estimate this ionization parameter, which basically tells us how much photon density there is from the radiation with respect to how much plasma density there is from the wind. So this ionization parameter is Xi, and it depends on the ionizing luminosity and the density of the gas and the distance to that gas. And the third quantity is line of sight velocity. Okay, so among other physical quantities that we can learn by studying ionized outflows, we can also say something about the geometric properties of these ionized winds and launching mechanisms, and maybe there are some correlations between these outflows and the continuum X-ray source. So those are the important parameters, and I'm going to show you how these parameters vary from one population of outflow to the other population of outflow. So let me start with the historically well-known UV absorbers. So it turns out that the majority of typical Seyfert ones and perhaps some of the quasars at cosmologically distant locations show intrinsic ultraviolet absorption features. And these are these have been observed by Hubble Space Telescope, as you can see here in the spectrum. Some of the most pronounced absorption features are Lyman alpha, of course, and then carbon-4 and nitrogen-5, and sometimes magnesium-2 as well. So as you can see from the spectrum, we see this emission line from carbon-4, for example. This is MGC 5548, one of the Seyfert 1. And if you zoom in to this very high resolution spectrum, you can see a series of dips, the troughs. So these are carbon-4 absorption features, which is slightly blue-shifted with respect to the emission line here. So that's one example of UV outflows. Now there's another outflows called the broad absorption line outflows, UV outflows again, in quasars. We see 10 to 20% of quasars exhibits these very broad absorption features, again, from carbon-4. So these are called the BAO. And people have seen these BAO UV outflows, for example, from Keck observations. When you estimate the blue shift by looking at the trough energy of this carbon-4 absorption features, the velocity is quite high. It can be up to 10% of the speed of light. So that's what makes this BAO quasars or BAO outflows very interesting. Sometimes these high velocity carbon-4 absorbers are accompanied also by X-ray fast outflows. And these X-ray fast outflows can be even higher, such as 40% or sometimes 70% of the speed of light. And I will show you that example later. So putting it together in this parameter space chart where you see quantum density, NH, on y-axis, and outflow velocity in the units of the speed of light on x-axis, UV BAO outflows. So this is the broad absorption line outflows. They occupy this space here. And so the ionization of these BAO outflows are low, and but it's very broad. So the width of these BAO outflows are more than 2,000 kilometers per second. And then this is close to 10% of the speed of light. Okay, so that's one type of absorption features that we see in UV band. And now here comes X-ray absorbers. Historically, these are called warm absorbers. NGC 3783, this is probably one of the well-studied Seyfert 1 AGN. And as you can see, it's clear that there is a series of chemical elements that imprints these absorption features at different charge states, a different ionization space. You can zoom in to one of the silicon band and magnesium band, and it's amazing how much grading spectroscopy, such as Chandra HETGS and XMMRGS as well, can see the detailed fine structures of these absorption features. So silicon, for example, you can see different charge states. It's clearly resolved. So is magnesium absorption features. And these are all blue-shifted. And by the way, you have to really have long exposure to increase the photon statistics to do this kind of study. So we need a lot of exposure time. For example, like order of hundreds of kiloseconds. But this allows us to study these atomic physics in the context of the absorption features. And the data seems to suggest that the UV absorbers and X-ray absorbers are somewhat related in terms of their velocities and ionization state. And they seem to be related to ionizing X-ray spectrum. So probably, probably X-ray spectral energy distribution is important to characterize these absorption features. Now, interestingly, the quantum densities that you can constrain from these absorption features here, they're not completely randomly distributed. Okay, that means that when you constrain the quantum densities, they are more or less the same order of magnitude, such as 10 to the 21 or 10 to the 22 atoms per square centimeters, despite the fact that the ionization parameter ranges over many decades in ionization parameter xi. So a lot of different ionization state for these gas, but the quantum density seems to be more or less the same. So that's this last point here at the bottom. Okay, now I'm not going to really focus on black hole X-ray binary systems here, but I just want to show you that it's not just the AGN that shows these kinds of warm absorbers in black hole X-ray binary systems, and also the neutron star low mass X-ray binary systems. We see a series of absorption features in X-ray band. For example, this GRO J1655 minus 40, it's about 7 solar mass black hole with a companion star. And again, from the Chandra observations, we can clearly see very rich absorption structures. Okay, and then I just want to say quickly the difference between the X-ray binary systems and AGN in terms of the wind properties. So these winds, they are almost all highly ionized. So there is no low ionization species here, partly because X-ray, the black hole X-ray binary has a very hard X-ray dominated spectrum. So all the ions, all the gas is very highly ionized. In order to explain, in order to model these absorption features, you need to assume multiple ionization zones and also multiple kinematic components. In other words, you cannot explain these absorption features by single ionization parameter or single velocity. You need some multiple components. Okay. Okay, so where do these warm absorbers show up in this parameter space? So it is down here. So again, we see these X-ray warm absorbers in Seyfert, AGN, and quasars as well, in addition to X-ray binary systems. The width of these absorption features vary from hundreds to thousands of kilometers per second. And as I said, ionization state of the gas also varies quite a bit, from minus log xi of -1 to 4 in the case of AGN. And so as you have probably heard from Francesco, we also learned another type of outflows, which is called ultra-fast outflows, because they are almost relativistic speed. And we see these very fast outflows, most notably in ion K-band in the form of hydrogen-like absorption line at 6.9 keV, and also the helium-like ion at 6.7 keV. And so here is some of the examples, and I cannot possibly list all the spectra that we see so far today. So these are just the examples. We see this prominent absorption features in ion K-band, and Francesco Tombesi is among the pioneering people to first discover these UFOs. And since then, we have seen more and more signatures of UFOs in X-rays in particular. So these are the velocity charts, and as you can see, they're not really slow. They're not even moderate speed. They are close to relativistic or more than 10% of the speed of light. Here is more examples. Again, you can see the dips, you can see the troughs in these spectra. Some of the objects are cosmologically distant quasars, such as APM 08279 at the lower right, and also MGJ 0414. These are high redshift quasars. So these are observed spectrum, and so that's why the energy is redshifted. But when you take into account the redshift, cosmological redshift, then these will be up to the ion K band, and also it's Blueshifted, and that's how we estimate the velocities of these outflows. And so it's very interesting that these AGN and quasars manage to drive these relativistic ultra-fast outflows. Now, one thing I haven't told you is that these UFOs also have a very massive quantum density. So the order of 10 to the 23 atoms per square centimeters, which is very distinctive from warm observers. And they are almost always highly ionized. So the UFOs are occupying this location in this parameter space. And then there are lots of works from many people led by Tombesi, Lahab, and Gafford et al., for example. Okay, now I want to show you another type of UFOs, not in very bright objects, but in Low-Eddington Seyfert AGN. For example, NGC 2992, this is classified as Seyfert 1.9. We know that it's not that bright. It's a sub-Eddington regime. This AGN has been seen by almost all the X-ray observatories so far today, including Suzaku, XMM, Chandra, and New Star. What's interesting about this source is that when the source is relatively higher flux states, such that the Eddington ratio is 2 to 4%, then we see UFOs. So it's relativistic speed and very massive quantum as expected, and highly ionized. Now, when the source becomes dimmer, even below 2%, then we don't see UFOs. So this case seems to suggest that the UFOs can be launched and the UFOs can be accelerated, not necessarily with high X-ray flux, because this source is clearly in a very low Eddington ratio regime, and yet we still see UFOs at the level of 2 to 4% Eddington ratio. So that tells us something about maybe launching mechanism. Now, ultra-fast outflows are known to be highly variable. So this is one of the prototype UFOs from PDS 456, which is almost near Eddington luminosity, from Matsu, Gabby Matsu, 2016. You can clearly see the variability of the X-ray continuum itself, but if you zoom in to the ion K band, where we see ion 26 ultra-fast outflow absorption features, the ion 26 UFOs is also highly variable in response to the continuum. There are some correlations that have been suggested from these outflows. So again, from PDS 456, which is close to Eddington luminosity, and there is another source, in narrow line Seyfert 1, IRAS 13224, we see ion K UFOs from these both AGN. Now, when you look at the change of outflow velocity as a function of X-ray luminosity, then it seems like there is a positive correlation between the velocity of the outflow and X-ray luminosity. So the brighter, the faster the UFO for both objects. Now, the strength of UFOs in terms of column density or equivalent width, it seems like it is anti-correlated. So again, as X-ray luminosity increases, the column density or equivalent width seems to be declining. So that's some interesting likely correlations. What about the X-ray continuum spectral shape in the continuum? So the Chardas et al. Has shown that in this APM 08279 that I showed you earlier, the gravitationally lensed quasar, bulk quasar, the velocity of ion K UFO seems to be positively correlated with the photon index gamma, the spectral photon index in gamma, and so is the column density NH. So in other words, when the spectrum becomes softer, then the UFO velocity increases, and so does the column density. So this is just one example, but it's a very interesting implication. Okay, now there's another likely correlation, this time with the strength of X-ray with respect to the UV flux. And in general, people use this spectral index called alpha OX. So that tells us the monochromatic flux ratio between 2 kb band and also the 2500 angstrom UV band. So as alpha OX becomes more and more negative, that means that X-ray is more and more suppressed. And as alpha OX becomes less and less negative value to the right, that means that the X-ray becomes relatively stronger compared to the UV. So in this work, I believe from some of the bulk quasars, they took the X-ray UFO velocity at the bottom, and interestingly, they also detected the UV winds, and so they compare how UV wind velocity and X-ray wind velocity is correlated with this alpha OX index, and it seems like a UV wind has this correlation. So as alpha OX becomes more and more negative, the velocity increases. I'm not sure about what to make out of this X-ray UFO correlations. So that's why I put the question mark here, but it seems like there is this correlation between UV winds and alpha OX. Okay, so I hope you have seen sufficient amount of observations to convince yourself that these X-ray outflows and also the UV outflows are abundantly out there. Now I want to introduce some of the theories and models that could potentially account for these correlations, or maybe some of the launching processes, starting with the thermal-radiative driven wind. Okay, so basically in this thermal-driven wind model, the disk needs to be illuminated by X-ray source, most likely from central corona, such that the disk temperature becomes high enough to launch the wind. And there is a critical radius called the Compton radius, which depends on the temperature of the disk. But this temperature of the disk depends on how much X-ray flux is received by the disk. So the wind can be thermally driven and accelerated outside this Compton radius, because that's where thermal pressure wins over gravitational pull. And inside this Compton radius, wind in general cannot be launched because gravity still overcomes the thermal pressure. So in this thermal wind model, the wind tends to be launched from larger radii rather than smaller radii. And sometimes this thermal wind has a hard time launching high quantum density. So it tends to carry relatively low quantum densities. And so some of the spectral modeling have been done in the literature based on this thermal disk wind models. Okay, what about the radiation field? So yes, of course, the radiation field can drive the disk wind. There are two ways to do it. If you have a really, really bright source, which is comparable Eddington luminosity or even super Eddington luminosity, you can use the direct continuum flux. And so this is the continuum driving wind, primarily due to the electron scattering. Not all the sources, not all the AGN have reached Eddington limit. So what happens if the source is in sub-Eddington? Well, if you have enough UV opacity, if you have enough UV flux in sub-Eddington sources, you can still launch winds from line emission photons. So these are UV line-driven photons, and it's not electron scattering that comes into play to accelerate the gas. It is the UV line photons. Now, there are some caveats about this UV line-driven mechanism, because the gas cannot be completely ionized, because in that case, there will be no UV opacity, so the gas cannot pick up enough momentum to be accelerated. So you have to avoid over-ionization of the gas. Some of the simulations, so these are state-of-the-art hydrodynamic simulations, and most of the simulations based on the UV line-driven scenario seems to be very narrow, confined region. In other words, if your line of sight misses this small angular window, you will not see fast outflows. And it seems like UV line-driven models cannot really produce very relativistic, moderately relativistic speeds. It can launch outflows up to maybe 10% of speed of light, but some of the UFOs have been observed to have more than 10%, 20%, 30%, or 50 to 70% in some very rare cases. So it's not clear how ubiquitously this UV line-driven scenario works for ultra-fast outflows in general. Okay, and so I think I will not talk too much about the details of these models because there is another competing scenario, and those are magnetic driving. If you have a global open field magnetic field, which is probably threaded to the underlying accretion disk, then you can take advantage of the Lorentz force, which is J cross B force, both from centrifugal components and also the pressure, magnetic pressure gradient from the toroidal magnetic field. So this is one visualization of one of the simulations of MHD driven disk wind model. As you can see, the density is plotted here on this poloidal plane. And at the bottom, we assume accretion disk, thin accretion disk as a boundary condition. So we're not solving the inflow and outflow simultaneously in this simulation, but we use accretion disk as a boundary condition. So the density of the wind is the highest at the bottom, at the base of the wind, which is this purple. And then as the wind gets launched along the magnetic field lines, which is this solid dark curves, density drops. And we don't have any winds in this funnel region, which is why it looks dark. In contrast, the ionization parameter xi is the lowest at the base of the wind because that's where you have the most material. And then as the wind gets launched along the z direction, then the ionization parameter increases. So the MHD wind in general has this two-dimensional parabolic streamlines. And because these magnetic field lines are physically anchored to the accreting gas on the disk surface, and the disk surface, because it rotates as the Keplerian motion, the wind is launched with the highest velocity at the smaller radius. And the wind that is launched from larger disk radius has a smaller initial velocity because of the Keplerian rotation of the disk. Okay, so in this MHD wind, we expect the high velocity components from farther inside, and then slower velocity absorbers from outer area. Okay, so here's a little backbone of the steady state axisymmetric 2.5 dimensional MHD formalism that we have been considering. So now I'm a little bit advertising our approach, and here you can see that the velocity in Z component is rapidly increasing at the expense of V phi, which is the toroidal velocity, as the wind gets launched towards higher vertical height. And like I said, the closer in, the faster. So in order to make connections with spectral analysis, we find this simplistic steady state MHD approach very useful because this allows us to better facilitate spectral modeling, which is something that the global, the fully dynamic simulations cannot really do. So that's why we employ this simplistic steady state MHD model so that we can actually say something about the spectral modeling. So we use X star to do post-process radiative transfer. So basically, we need to assume some input initial X-ray ionizing spectrum, such as this one in the case of PDS 456 in X-ray band. And then we use this input SED to calculate the radiative transfer along the line of sight. Okay, so this is how we pass the radiation field from one cell to the next cell along the line of sight in order to calculate the column density of various different chemical elements such as iron, magnesium, silicon, sulfur, and so on and so forth. And we calculate the absorption spectra using a Voigt function, which requires this photo absorption cross-section and the column density of the produced ions. So this is how we do spectral modeling to construct a template spectra based on some SED and also the MHD wind structure here. Okay, so just to pick up the speed, the generic features of MHD winds include that morphology of this MHD wind is relatively luminosity independent because the driving force is J cross P. It's the magnetic field, the centrifugal force, and the pressure gradient of the magnetic field. But it is very susceptible. It's very dependent on the ionization state and also the input SED for the outcome. And because the model is mass invariant, this can be applied to both AGN and X-ray binary systems. Okay, so I just want to emphasize here again that the wind density and ionization distribution is very, very sensitive to the input SED. So in a nutshell, you can almost approximate the density structure such that there is this angular dependence of the density structure from MHD model using this self-similar radial dependence. So we have been using this prescription in the context of the MHD wind to make the spectral analysis. Now, from the global perspective, just want to briefly touch that the mass outflow rate goes like R to the 1/2 in this context, but the kinetic power goes like R to the -1/2. So that means that the most of the mass has been lost predominantly from larger distances, whereas the energy which is delivered by these winds are predominantly coming from smaller distances. So this is another characteristic features of MHD wind. Okay, so this density P, which is this, the density slope P, this has the consequence of how much quantum we expect. So when P is 1, we expect to have almost the equal amount of quantum density from these different chemical elements as a function of ionization parameter. If P is different, the quantum density is produced in a different rate. So we apply this to a number of sources. The NGC 3783, again, this is SafeWork 1 AGN. We made the template spectral models, and here is the best fit. We found that the P of 1.15 has the best match, and this density profile is actually consistent with the previous literature work using the so-called absorption measure distribution. I'm not going to go through this, but this density slope at the global scale seems to be consistent with the other work. And notice that these ions, these absorbers, from shorter wavelengths to longer wavelengths, they are not independently fitted because they are coupled to each other in a mutual fashion, because all these ions are living in the same continuous wind. So we don't have a freedom to change quantum densities of these ions independently. These are all coupled. So it's a very tight model. Okay, now UFOs, we also try to model this UFO in PG1211. Again, the slope of the density gradient is 1.14. And we try to fit this ion K absorption features here with the ion 25 species. And we estimated M dot and also E dot, which is consistent with the previous work. PDS 456, which produces the prototype UFOs, as I said earlier, we also fit it with a P of 1.2, and the centroid velocity is about 35% speed of light. Now I have a number of different velocities to explain this absorption, this UFO feature, because we are dealing with the continuous wind, and this continuous wind has a velocity gradient. So we cannot really specify one single outflow velocity in this context. Okay, so I'm almost coming to the end. So there are some predictions that our model can make. So for example, by taking ion 25 and the carbon 4 from our simulations in the context of MHD wind, we see these correlations. which is actually consistent with the previous observations, as I mentioned earlier. This is a busy plot, but this blue part shows how ion 25 velocity is correlated with gamma. And this pink curve here, pink circle, shows how UV absorption feature carbon-4 is correlated with alpha OX value. And they seem to be consistent with these observations. We also made predictions of the velocity of the UFOs and quantum density of the UFOs as a function of X-ray luminosity. And that is also broadly consistent with the previous work for example, PDS 456. So the velocity increases as X-ray luminosity increases, but the quantum density drops as X-ray luminosity increases because of this ionization equilibrium. Now, there are some challenges that we'd like to address in the future work, such as the multiple fast ion K UFOs. So it seems like there are multiple fast components, not just the 10% of the speed of light, but even higher, faster outflows. Some of the UFOs, they don't necessarily have high quantum density or high ionization parameter. They are all relativistic, but some of the UFOs seem to have very low quantum density and also low ionization state. So these are non-canonical UFOs, such as these, the green ones here in this PG 1114. We still don't know how to make these non-canonical UFOs in comparison with the classical UFOs, which has higher quantum density and a higher ionization parameter. In X-ray binary systems, on the other hand, the UFOs are not confined to the equatorial region. There seems to be some sources of non-equatorial inclination angle, like 30 degrees and 40 degrees, and yet they are almost a relativistic 10% of speed of light, such as EXO 1846 and MAXIJ 1348. So we have been trying to model these non-equatorial X-ray binary UFOs because it's very difficult to explain these non-equatorial UFOs from thermal-driven and line-driven scenarios. So this is still ongoing work, but we're trying to explain this as well. Okay, so the future work, microcalorimeter is definitely instrumental to revolutionize our understanding of these observers with the CRISM and Athena. And of course, CRISM goes first, but Athena has this crazy effective area. So that will be really, really exciting. So we did some simulations for AGN UFOs, assuming 10% of the speed of light. And clearly, microcalorimeters are able to resolve these fine structures, both from CRISM resolve and Athena X-IFU. The same for binary systems, black hole X-ray binary systems. Now I want to just quickly emphasize that it will be really interesting to finally resolve ion 26 spin orbit doublet, which is due to the quantum mechanical spin effects. This is currently not really resolved by Chandra resolution. We should be able to do this with the microcalorimeter data. And when the source has very weak elusive absorption features, the microcalorimeter should be able to detect even these weak absorption states. So finally, just for the last 1 minute, can we distinguish different launching mechanisms? Well, the answer seems to be yes. So maybe for AGN UFOs, we could look at the spectral shape in details and whether the red tail is extended or blue tail is extended. We might be able to tell whether it's a UV line-driven wind or MHD-driven wind. in black hole X-ray binary winds, there is a suggestion that the thermal driving wind tends to produce narrower width compared to the magnetic case. So that might be a telltale to distinguish these different launching mechanisms, which have been addressed for many, many years, and yet we still don't know what is really the main driving mechanism. So that would be really interesting question to be answered with the future microcalorimeter observation. So here's a takeaway. We see these disk winds in X-ray in different systems. We have warm absorbers and ultra-fast outflows, but there are very many unknown subclasses of UFOs, and we'd like to understand these outflows with the state-of-the-art next generation observations of microcalorimeters. So I'll stop here and thank you for your attention.